Hello, and welcome to today's session, Virtual Platforms to Shift Left Software Development and System Verification. Really like to welcome you here and say what a great time I'm having seeing all of you and attending my first face-to-face conference in almost 2.5 years, but we're not. I'm recording this in advance, and you're all sitting at your desks just as I'm sitting at mine. It's kind of a disappointment. But I hope to resolve that disappointment by some great content. My name is Ross Dickson. I'm joined today by my co-author Pankaj Kakkar, and today we are helped out with our demos by Akit Rana, and all of us work for Cadence Design Systems. Today we're going to talk to you about how to improve your system verification by using virtual platforms and a software-driven methodology. Now, some quick background here. We all know the problems. Designs have gotten more complex, up and to the right, show a nice exponential curve here. And we see that the problems are getting more difficult. We also see our next exponential curve that the later in the design we find a problem, the more it costs to fix it and the more time it takes. We just love exponentials. But we then get to the point of solving problems earlier means they cost less, and because they cost less and take less time, you can get more of them per day. And if we've got an ROI mindset, we can go, aha, I make a more effective product more efficiently at lower cost if I find problems earlier. Thus, we want to always increase our verification. All right, we've all seen this before. That's wonderful. Every ADA vendor ever has said pretty much the same thing. So let's move on to something more interesting. The solution. Oh, there we go. We're going to shift left and solve the problem. Well, what do we mean by shift left? Well, we need a baseline. Traditionally, you have begun your chip development, you have verified your design, you've brought your silicon in-house, you've done bring up, and then you run some software on it. All well and good. And from there, the obvious solution and the way you make this better is you introduce a virtual platform to begin your development earlier, so you run your software as part of your verification, thus shifting left your flow. All done. We can go home now. Oh, wait, we can't? Oh, right. You've seen this before. In fact, you've probably even seen me say this before because I've presented virtual platforms and a software-driven methodology at DVCon before. So why am I up here? Well, not just because I like traveling to California so much. Oh, wait, I didn't travel to California. Right. But why am I here? Right. I'm here because we actually have something new to tell you, that it's not just about a virtual platform, but that we can actually do more efficient solutions. So let's look at that in another way. So instead of just that simple shift left, let's look at a timeline here. In our traditional flow, we've developed our hardware, we've verified it, we've taped it out. Sometime later, we've gotten a sample in, we've done our software bring up, we've done our software dev, we've done our system verification, the product has shipped, yay, all is well and good. Then we brought in the virtual platform. Now, we put together a model early on in the process. It's probably abstract and doesn't represent our final design, but it lets us do some software development until it doesn't. What many of you have found is that without being a representation of the final model, we have to pause until we've gotten far enough along in our hardware development to bring in a virtual platform of the final model. We might say, yeah, I don't like virtual platforms. You guys, you're never accurate enough. I went straight to the emulator. That's great. I love emulators. We sell a lot of them. But again, you need your design to be reasonably complete if you want to run any software on it. Yeah, no, the emulators are too slow. FPGA prototypes, also good. We like those too. Same problem. You need a complete design before they can really run much in the way of software. So that brings us to the hybrid. Here, we combine the values of the virtual platform with the emulation and the FPGA prototype. You start with that abstract model and you incrementally make it more detailed, and you can bring in the emulators and the prototypes to provide more detail at the highest possible performance. And this allows us continuous validation as we bring up our system. As a new component gets developed, you bring it in, integrate it into the platform, and validate it in context. Now, so far, motherhood and apple pie. Let's look at a little bit more about where we are, where we have applicability. Because I can see some of you getting a little restless in the back. Stop that. Stay here. We're going to get interesting. You've said, but virtual platforms don't solve my problem. And that may well be true. You know, today we're talking about our virtual and hybrid platforms. We have products in other areas. Say you need a new piece of IP. Great. You need to verify that IP. Great. These are not the tools we're talking about today. You integrate that into a system. Virtual platforms don't really address the SoC level integration and verification very well because they tend to be abstract models, not the detailed RTL which you're trying to solve. Well, we all know that emulators and prototyping boxes do a great job of that. We bring them in with the hybrid. To learn more about those details, we have other presentations for you. Today we're focusing on the virtual and the hybrid platform. Virtual platform is available early in the system, and it could extend to the right, but it would get in the way of the rest of the words on the slide. But it's really focused on the OS and the middleware. And depending on where you're going, it may support some of your apps, it may support most of your apps, or it may not give you enough performance if you've got a very high processor count. And it goes down into the drivers and firmware to some degree, but it's not a fully accurate platform. We've said that the emulators and the prototypes, they're great, they're fully accurate platforms, but they don't have the performance for the OS and the middleware. So what if we combine these two into a hybrid so that we can address a full software stack with enough detail for our firmware and our drivers? So that's where we're going to go. But before we get there, I hear a problem creeping up. You there on the right, or were you on the left? I sure wish these headphones were in stereo. Much easier to tell where the questions are coming in. You're saying, but how can I build a virtual platform based off of my final design when my final design isn't done until I've done my verification, which I've shifted left with my virtual platform? Don't I have a circular dependency here? Well, you would if you only ever built your final design. But part of our software-driven methodology is to say that that's not actually what you need to do. You can build an abstract design and successively refine it over time. So let's say we'll start with a fully abstract design. You know that your design has some kind of CPU core in it. It's got a modem for communication. You're going to design a custom accelerator. That's how you differentiate from your competition. You got a couple IOs with custom drivers, and it's all connected with a network on chip. Great. We'll start with an abstract design. But what is an abstract design? Is that just something that looks like a CPU but doesn't actually compute code? No, really what it is going to be some arbitrarily chosen design that is real. And you might say, well, but that's just the example model that came with the virtual platform. Good catch. That is exactly what it is. That we recommend you start with a virtual platform that has an entire library of reference designs that you can choose as your abstract starting point. You find something that looks right. It's got the right kind of CPU. You might say, I don't know which core I'm going to use, but I know it's going to be ARM, and I know it's going to be 64-bit. Or maybe it's RISC-V and 64-bit, or maybe I'm going for old school and doing 32-bit in real time. Whatever, we've got you covered. So you pick something that's about right, and you bring up your software. Are you done? Well, no, you've just booted the start here example in the documentation. What you do then is where things get interesting. So you've got a couple different design teams. You've got one team working on building the custom accelerator and integrating it with the correct CPU core. Great. They get to work building their custom accelerator. They've got an abstract model of that. They plug it in. Good to go. You've got another team that's building that first I/O device for you and building its custom driver. Or perhaps they've selected an I/O device and are building a custom driver. Either way. And then you've got another team with the next I/O and the next driver. And this can propagate. 3 fit on the slide. Maybe you have 4 teams. Maybe you have 7 teams. Maybe you have 2 teams. Either way, What we're doing here is we're saying you've started with a reference platform provided with your virtual platform that boots an OS and has drivers. You then swap out one component and integrate it in and work on the drivers for it so that you validate it. And you do each of these, and as the designs successively get more complete, you can integrate them back in until eventually you've integrated all of the pieces together, and you no longer have an abstract system. You have a complete system that matches your final design. But this doesn't happen until late in the design flow while you've been productive the whole time. So we've broken that cyclic dependency of you must have the final design before you can build a complete system platform. But wait, I hear you saying. Okay, maybe I don't hear you saying it. I'm imagining you saying, but wait, I imagine you saying, what happens if I've built the best accelerator ever, but I didn't build an abstract model? Well, we could say shame on you and slap you on the wrist for not building an abstract model, but that doesn't do you any good. So instead, we'll say, well, this is where we bring in the hybrid. You've got the detailed RTL because that's what you just built. That's what you're going to tape out. You put it in your emulator, you put it in your FPGA prototype, and you integrate that with your virtual platform to give yourself a hybrid environment. Now, this hybrid environment could be there just because you don't have the abstract model. Or maybe it's because this accelerator, the key part of it is that you need to test it in a software context and it needs to be accurate because you need to know, is it fast enough to be faster than just running on the CPU? Well, you get that level of accuracy with your hardware products, but you don't need that level of accuracy for everything else. CPU, you've profiled it, you know about how fast it runs, and you bought it commercially anyway. You don't really need to revalidate that macro. Well, put it in the virtual platform, tweak the knobs a little bit to get it about the right speed. But put your expensive prototyping hardware onto the expensive problem. Focus on the design under test, not the commodity that you've used before. So, with that, we're now going to start a transition from my high level, this is what we're talking about today, to a detailed walkthrough of how you use a suite of Cadence products to do this methodology. So we have an example system where we're going to, in our end, we're going to have a couple of CPU cores and a couple of clusters with an on-chip interconnect with timers, UARTs, memory controllers, all of that in the virtual environment, connected via a number of virtual bridges and hybrid bridges into a Palladium emulation box, which has then some of the I/O peripherals. It's got a lot of the low-speed things. It's got a GPU and other pieces in there connected together with our smart memory technology so that the two sides stay in sync. And this then allows a useful environment. We'll see how we can use this to use the environment to quickly assemble this, select pieces, bring them in, and give us an environment where we can do our software debug in a unified environment that lets us bring up our software where some of it is running on the virtual and some is running on the emulator, and it all just works, and you can debug and see everything and run your verification environment to be as productive as you can. And with that, I hand off to my colleague.
Hello everyone. I'm going to talk about typical hybrid platform creation flow, which will enable the software debug on Helium. For that, we'll start by creating a new hybrid platform by utilizing the built-in reference platform as a starting point. We can save the platform and build on top of it by adding new models as per the requirement, by utilizing the various base models provided in the Helium library. Remove the unwanted models from the platform, configure the model parameters as needed, and then we'll talk about how do we handle the port bindings, interrupt connections, and the memory map in the platform assembly. How do we add RTL stubs to stub specific RTL accesses? How to configure the hybrid adapters, which eventually allows us to connect to the RTL design. And then we'll talk about how do we integrate the pin compatible RTL CPU wrapper, chick wrapper, and the smart memory by replacing the existing CPU interrupt controller IP and the RTL memories from the RTL design. And then we'll talk about how do we build the platform and run Linux on hybrid platform and start doing software debugging. Okay, as you launch the Helium, the very first view you would see is the Helium model catalog is pre-populated in the GUI. As I explained, it will provide you various base models and the reference platform. You can pick any of this reference platform and start building your new platform on top of it. As you open the platform in the design editor of the platform assembly, adding and removing of the virtual model is very easy. Just simply search with the model that you want to add here in this particular box. As you filter out the model, just double click on that. It will add the model in the platform assembly. Configure the model as per your requirement. There is also a possibility of adding the vectors of the model by clicking on this particular icon. Select the number of vectors that you want to add. It will add that particular model inside the platform assembly. Helium also provides to copy the multiple group of models altogether and paste it in your new platform. In this case, there is no need to do the reconnections between the components and no need to set the parameters. Helium will take care of that automatically. What you need to take care is the external connections to the other models in the platform assembly. Now, Helium platform assembly provides the easier way to visualize the parameter of each and every models that we have in the platform assembly. In order to configure the parameters of the models, just look out the parameters and just click on the value and set to the value whatever you want. Now let me talk about how can we handle the port bindings between two models in the Helium platform assembly. There are two ways to do the port binding. In the first method, Helium has provided a dedicated port tab wherein you can search for a specific model and the signals that you want to connect. Once you select the signal, it will show you the possible bind candidates wherein you can establish the connection. Select these two signals and right click and select bind selected port. It will establish the connection between these two signals. Now the another way is to just right click on the unbound port. It will show you the context wherein you can navigate through a specific target socket and select that particular target. Click on that. It will establish the connection between them. Similarly, you can unbind the interrupts and connect the interrupts between the models and the interrupt controllers. So this is the easier way to handle the port bindings between the models. In Helium platform assembly, there is a dedicated memory map window provided wherein we can create, view and edit memory maps of each and every models that we have in the platform assembly. You can easily change the value of the assigned address to the newly desired value as per your new requirement. It provides you the base address and the size of each and every models that we have in the platform assembly. Now let me talk about how can we handle the memory map of newly added models inside the platform editor. Once you add new models, just right click on that and select add to memory map. This way you will be able to assign the entries of new models inside the memory map window. The default value assigned to that model will be 00, which you can configure to the new value as per your requirement. Once you assign the memory map to the newly added models inside the platform, Helium also provides the way to validate the entry and make sure that the assigned address is not overlapping with the previous one. Once you are done with the validation, you can click on reconfiguration button, which is this green color button. Once you click on that, it will generate the actual connections between the C router and the targets. In the early phase of the development cycle, when specific RTL IPs are not integrated in the design, Helium supports to stop those RTL accesses and continue with the software bring up using the same images without really altering the software images. just click on this particular icon. It will add the stub and assign the right addresses to that particular stub. Helium will ensure to stop those accesses and not allow the transfer to go to the RTL IPs. Once the RTL IP is available and integrated inside the design, we can choose to remove those RTL stubs, and that way the accesses will go to the RTL and we can validate that RTL accesses. Now, what is hybrid adapters? The Helium model catalog provides the interface component to enable the connections between the virtual models and the RTL designs. Virtual models are basically running on the host machine side, wherein the RTA design can be running on the Xcelium simulation, Palladium emulations, or on the prototyping of the FPGA, which is basically on the Proteum. Helium adapters provides the mechanism in order to connect the virtual models to the RTL sides of the design. So there are two parts to it: virtual side of the adapters and the RTL side of the adapters. Now let me talk about how many virtual side of the adapters that we have in the Helium model catalog. So there are varieties of adapters that is supported in the rich libraries of the Helium. Those are nothing but CPU adapters, which is pin compatible with the existing CPU architecture, jig adapters, which is pin compatible with the jigs 400, jig 500, jig 600 version of in the interrupt controller, smart memory, which basically enables the faster and the concurrent and the transparent view of memories between the virtual and the RTL side of the design. We have bus protocol specific adapters like based on the ACE, AXI, AHB, and the CHI protocols based adapters, which is nothing but TLM to RTL and the RTL to TLM adapters that is provided by the Helium libraries. And it also provides the signal level adapters. In order to add these hybrid adapters inside the platform, just search with the adapter name here in this particular text box. Once you find the adapter, just double click on that and it will be added to your platform in the design editor. Configure the adapters as per your requirement, which will enable you to establish the connections to the RTL design. So once we are done with the hybrid adapter integrations inside the platform, the next step that we have to do is to configure the RTL path parameter of each and every hybrid adapter with the associated hierarchical path of the RTL side of the adapters. For example, we would have integrated the CPU RTL wrapper, interrupt controller wrapper, and the smart memory wrapper inside the RTL. So those hierarchical path inside the RTL design needs to be configured here in order to establish the connection between the virtual side of the hybrid adapters to the RTL side of the hybrid adapters. For example, in this case, jig 600 bridge is essentially connected at this hierarchical path where the jig 600 RTL wrapper would have been instantiated. Similarly, RTL CPU adapter is configured in this particular path where the RTL CPU wrapper would have been instantiated. Similar thing applies for the bridge and the smart memory. All right. So far we have just talked about how can we deal with the virtual side of the modifications in the hybrid platform. Now let me talk about the changes that we have to do in the RTL side in order to bring up the hybrid platform. So there are three important changes that we have to do in the RTL side. First, replace the existing RTL CPU IP with the pin compatible CPU wrapper, which is provided as a part of Helium install. And then replace the existing interrupt controller IP with the pin compatible jig 600 CPU wrapper. And the third one is replace all your RTL memories with the smart memories, which is provided as a part of Helium install. Now let me talk about the diagram what I'm showing you right now. The green color part what you see is the virtual part of the hybrid platform, and the blue color is the RTL side of the hybrid platform. wherein we have replaced the existing CPU IP with the CPU wrapper, which is provided as a part of Helium install. We have connected the ARM Theodol Dynamic IQ wrapper here, which has essentially AXI peripheral master, CHI master port, signal adapters, and the AXI slave utility BFM within the CPU wrapper. Now this is the JIG 600 bridge, which is the JIG 600 wrapper that we have replaced with the existing interrupt controller IP. Similar thing applies for the smart memory integration. Integrate the smart memory inside the RTL and provide the hierarchical path to the smart memory model in the virtual platform. All right. So at this stage, we are ready to build the platform. In order to build the platform, we have to provide all the right build options in this particular text box, and then provide the build configurations as Palladium as needed. You can choose Xcelium also or Protium also based on your need. Provide the RTL snapshot location in this particular text box and just click on OK and perform the platform build. On the successful completion of the platform build, we are ready to run the platform. Now, once the platform has been built successfully, as we run the platform, it will start loading the design on the Palladium, and this particular GUI will be invoked. Once the design has been loaded successfully, it will start running the Linux boot, and you would be able to see all the messages coming on the UART console like this, and eventually it will boot to the Linux prompt. We can log in with the login ID and the password and execute a couple of commands. I'm going to show you this particular Linux demo in the actual demo. Okay, so before I switch to the demonstration, I would like to quickly introduce the Helium software debugger. This is the typical view of the Helium software debugger. Helium software debugger is the standard Eclipse-based software debugger wherein it provides all the basic features that any Eclipse-based software debugger would provide. Let me quickly introduce all the different windows of the debugger. This is the debug window wherein we should be able to see all the multiple cores available inside the platform. Once you click on a specific core, it will change the perspective of entire debugger, and we should be able to see the debug views with respect to that particular course. Here it shows the session control. We should be able to run the free software debug, or we can pause through this command. We can perform the step in and step out using this particular icons provided here. This is the system viewer wherein we should be able to see all the models associated in the platform along with the CPU cores. Once we click on that, it will show you all the properties related to that particular core. This is the file browser wherein we can browse through the different source code, and we can open and we can visualize in the source browser. This is the register window wherein we should be able to see all the registers values associated during the software debug. Similarly, in the variable view, all the C variables, all the registers that we can see inside the variable viewer. This is the breakpoint manager where during the software debug, wherever we are putting the breakpoint, probably in the C code or disassembly or in the outline or any function level, breakpoints that we have kept anywhere, all the breakpoints would be managed by this single breakpoint viewer, wherein we can enable, disable all the breakpoints from the single location. This is the disassembly viewer where all the disassembly level code we should be able to see during the software debug. Now at the bottom here, we can see the current core being selected during the execution. And this is the Linux path being selected at this point of time. Here we should be able to see the number of instructions being executed so far for a specific core. This is the console window where we can enter all the different DCL commands or the ESW commands during the software debug. Now this is the memory viewer where we can see the different memory, different addresses in the platform. So this is the basic introduction about the Helium software debugger GUI. Now let me switch to the VNC and let me show you the demonstration of the Linux boot. All right, so I have already launched the Helium, and let me just quickly introduce the different windows of Helium GUI. So this is the catalog browser where we can add different catalog. This is the pre-populated Helium model catalog that we were talking about. We can find different models here and we can search whatever the model that we want to search, and we can add those models inside the platform. These are all different examples that we are providing as a part of Helium install. This is one of the example that I have invoked it, and this is the platform. Once we invoke the platform, all the models we should be able to see here in the design editor. These are all different models that we have, like core, jig. This is a bridge, which is essentially AXI based TLM to RTL bridge, and all those adapters that we have talked about in the slideware. This is the memory map window where we can see all the different memory map of all the models that we have inside the design. We can change the address as per your requirement quickly just by double clicking on that. All right, now let me start running it. So in order to run, you should just go to run and click on run platform. But I would like to launch the Helium software debugger. So before that, let me just switch to the software perspective. So there is one small icon here. Just click on that Helium software debug. It will switch the perspective from Helium platform assembly to Helium software debugger. And this is the typical view of the Helium software debugger. Now, in order to launch the debug configuration, just click on this menu and click on debug configurations. Here, we should be able to provide different debugging configurations by just simply selecting the platform and just providing the image and the source symbol. We can provide the corresponding run commands very easily from this window, and whatever the external arguments we want to provide, we should be able to quickly provide here and start debugging the software. Now let me just click on debug. Once I click on the debug, it will start invoking the Palladium window, wherein it will start downloading the design on the Palladium box. It might take a couple of minutes. So once the design has been loaded successfully on the Palladium, we should be able to see the connections will be established to the Helium software debugger at the beginning of the source code. And from there, we should be able to start doing the software debug. Now we can see the design is being loaded on the Palladium GUI. All right, so now I can see the design has been loaded successfully, and at the background, I'm able to see that the disassembly window has been popped up with the arrow mark here. That means it is executing from the 00 location. I do not have any source code right now available for this example, so I would leave with the disassembly level debugging right now for this demonstration purpose. Now, as I have introduced the different windows already, this is the debug window, this is the project browser, these are all the different control wherein we can start running, pause, step in, step out, the current status window here. This is the system level window wherein we can see all the different models associated. Once we click on that, all the properties associated with that model we should be able to see. And of course, we can see the registers, we can see the variables and all the breakpoints that we are putting during the course of software debug. Now, let me just quickly put one breakpoint here. Right, as you put on the breakpoint, you should be able to see that breakpoint manager is showing all the breakpoints. Now let me just click on run. Once you click on run, it started executing and stop at that particular breakpoint, wherein we can see the current status here, the stop at CPU 3. and the reason was software, right? Now let me just remove that breakpoint by just double clicking on that, and let me give you free run here. Just remove this breakpoint as well. Right. Now, this is the free run what I'm doing right now. As you run, you should be able to see all the boot messages are coming freely, very smoothly on the UART terminal. The response of printing the messages on the terminal is also pretty good. This might take a couple of minutes to boot the Linux successfully and reach to the boot prompt. Let's wait for a couple of minutes. Okay, so we are successfully able to reach to the boot login prompt. Now let me just enter the login ID and password. Okay, so I'm able to log into the prompt. Now let me just execute a couple of commands. CPU info. Okay, so with that, I'm able to enter the command, and it's basically printing all the CPU related information. Now let me enter proc mem info, and it is going to print all the information related to the memory, right? So with this, let me conclude my demonstration. So we are successfully able to boot Linux, and I have shown you the demonstration of how to connect the Helium software debugger. And I have shown you how to build the hybrid platform using Helium platform assembly. Thank you so much.
Thanks for that great demo. I hope you can see how this can help you quickly and easily assemble a virtual and hybrid platform and use that to increase your verification throughput and produce a better system more easily than through a traditional development methodology. If you have any questions, please ask away. That completes our pre-recorded portion of this. I sure hope we have some questions. You've been a little quiet on the chat window. Feel free either to raise your hand or unmute yourself or type something in here. Anything else we can tell you about how we can help you move your verification environments earlier in time and make things work better? And
so there's a there's a question on where does PSS fit into the picture. So basically, the portable stimulus part is something that would generate an embedded test or a C test, and that is something which we would use as an image that would run on top of this platform. So depending on the kind of virtual or hybrid platform you're running, you essentially would generate your stimulus, and that stimulus would compile into an image which you run on your platform.
Would it be possible to define a virtual prototype that operated just in terms of the PSS action list and the block functionality, and abstract away all the bus architecture and registers that
in principle, yes. I mean, you should be able to build something as a pure virtual to the extent that it's able to do the actions that you've defined in your PSS model. You basically would need your model to be able to do that. Like for the CPU execution, you would typically, I mean, if it is ARM, you would pick up a fast model. And then for the other models, I mean, depending on the level of abstraction you need to handle, you should be able to pull a model and assemble a simple platform together.
Are there any examples of something like that available?
With the PSS story, I mean, if there's something specific, we can have a session for you, Jonathan, to help with that. I mean, there are examples available, but not really connecting the PSS story in that. So I mean, we can do something, basically talk to you offline and help you with that.
Yeah, that might be a good idea. The last time I tried to run in, I tried to run PSS, I had license access issues here at Qualcomm, which didn't quite make sense to me at the time, but I didn't have time to work on it.
So Qualcomm does have the PSS set up and Perspec in, and the licenses should be available. So in principle, you should be able to create your portable stimulus. The only thing is you need to make sure that your portable stimulus actions and all of that is sort of aligned with the platform that you finally want to run on. So, yep, I mean, we can help you with that.
Is there an action communication, infrastructure available for virtual prototypes? For for communicating the action into the C code or system C code.
So the way the actions, I mean, it depends on how you really model your action and the exec block for your actions, right? What needs to be generated as part of your action. So, and then the model that you have should have the ability to run or execute your action. So that's something that, I mean, for the embedded CPU, it's just C code, embedded C code that gets generated out of the action. So it will run out of the box on any platform abstraction. For the rest, I think your model needs to.
All right, so we had another question about the look and feel of the debug environment. The question being, does the Helium debug environment look the same as the Indago embedded software debug tool? And at the moment, the two tools are similar, but there are a number of differences based off of the fundamental execution mode. At present, Indago is optimized for post-processing a debug trace rather than a live process from the while the emulation or and hybrid are running, whereas Helium is optimized for the interactive flow. We're actively soliciting customer feedback now to understand where it would be useful to combine these two flows, or if they're seen as separate but complementary flows. And we'll be optimizing the look and feel based off of that feedback. We know what we like looking at, but fundamentally it's what's going to be effective for you. So similar, but not fully aligned at the moment, but we will be updating products to give a common user interface so that there's no confusion as you move from one to the other. But we need to know where you're going to be using this and how that use case exists so that we can give you the best experience. Other questions from anyone? Now, it's sounds like it's the final presentation after a reasonably long conference, and everyone got their questions out early at the panels. I hope we haven't left too many of you too confused about what we can do here and how this can help. A question for you as the audience, how do you see this fitting into your workflow? Do you see any gaps, or is this revolutionary, or is this, oh yeah, we're all happy customers and we just wanted to see if there was anything we hadn't seen since the last build?
Well, I'll speak for myself. My gap is that this whole RTL subsystem is an implementation detail for me.
Yes.
I want to be able to work with the upstream teams to define how my block is supposed to be operated in terms of the messages, so that then I can be sure that this whole digital block implements what they need. That we have the actions defined that they need, that we can get into and out of all the modes they need my block to get into and out of. And so that's why I'm looking at virtual prototypes. And also, I am looking to get them to start adopting PSS.
Yes.
I think makes sense. I think, Jonathan. Right now, I mean, there isn't really a natural or an automated connection from PSS to really knowing its actions and then have the ability to translate into generating a model. That's to be done manually, but yeah. Yes, it can support multiple debug sessions.
Yeah. So in that debug question going further, are you asking simply, can we run multiple separate jobs in parallel on the same emulator and have separate users debugging separate sessions? To which the answer is yes. Or is the question, are you looking to have multiple users connected to the same job and basically having, a team debug session on a single problem? And that also works. But which use case you're specifically interested in will help us make sure that we answer any particular questions you have there. All right. Well, unless anyone else has any other, there we go. Multiple independent debuggers. Yeah, so you can, if you have multiple jobs running on the emulator, you can connect multiple separate debug sessions without any trouble. Basically, you can think of each virtual platform and emulator hybrid as a separate virtual prototype. And this uses the partitioning built into the Palladium or the Protium for your hybrid, so that each job is fully independent and can be debugged as independent sessions, so that we provide the full utility that a user has come to expect for each individual job.
So you wouldn't have a typical limitation of basically having a real debug target connected, right? So on the Palladium emulator, because in this case it's a caddy-based debug, so I mean there are multiple sessions that would be allowed, and you should be able to have multiple users do that.
Yeah, that's a good point. This is not a, there is no, we don't have the, you're not plugging a probe into a JTAG sitting on the side of the emulator. You're making a software connection. So we don't have the how many physical things can you plug in at once challenge. All right. Well, thank you all for attending. If we didn't get any questions answered or you want to see more detail, please feel free to reach out to us. You can get at us through the attendees links in the DVCon hub or whatever the core application is called, and send us email. Or, well, you found our names. You can probably find us through the Cadence website pretty easily if you need us that way. Please feel free to ask questions. We'd be happy to answer them. And if you need another demo, or if you want to bring this insight on site for your colleagues, let us know. We're happy to support you in improving your verification. But I don't know if there's a closing reception or anything like that from DVCon. The organizers didn't give me that, and I can't find my agenda behind the Zoom screen here. So thank you all for coming, and wish I'd seen you all in person. These presentations are kind of a challenge to do via recording.